Swayam Prabha. Digital India. Educated India.
Welcome back to this another session of Introduction to Aerodynamics, and in this session we will be continuing with the airplane parts part of the presentation. As you remember, in our last lecture we talked about the effect of leading edge sweep, and I said that the part of the reason for leading edge sweep was that as aircrafts became faster, like say the present day aircrafts compared to that of the first and second World War era. Now, as aircrafts have become faster and aircrafts are flying at closer to sonic speeds, like most of the civil aircrafts, civil transport aircrafts. Of course, you have there are aircrafts that fly faster than the speed of sound and aircrafts that fly several times faster than the speed of sound, but most of the commercial aviation still flies at near sonic speed, and the sweeping of the leading edge is just a trick to make the aircraft fly at high enough Mach number where a straight wing or a like unswept wing would have seen would have crossed the drag divergence Mach number. I have not talked about what is this drag divergence Mach number, but we will come to that at later presentation. But just at this point, think of it as a Mach number, free stream Mach number, where the drag on the aircraft suddenly becomes extremely high. It is close to the sonic speed. It is so there is something called the critical Mach number. So, critical Mach number we have it's let me just talk about critical Mach number. So, there are these important. So, Mach number as we have been talking about is u by a. You can think of u as flow speed, speed of the flow by the local speed of acoustic disturbances. Also we say speed of sound, but think of it as the speed at which acoustic perturbations propagate, because you will see that there is a physical significance to that, the speed of the flow with respect to the speed at which acoustic signals propagate, because you can already think about this in this way, that if the speed of the flow is faster than the speed of these disturbances, then these disturbances will not be able to catch up with the flow. Okay? The flow will go faster than the, but however, if you have a situation where your so u by a So, three situations can arise. One is m is less than 1, one is m equals to 1, and one is m greater than 1. And when m is less than 1, your acoustic fluctuations are moving faster than the speed at which the flow is moving, right, because a is greater than u, m is less than 1. Then you can reach a situation where you crank up your flow speed, your temperature is the same. So, now your flow convection is happening at the same speed at which these waves are moving. So, with respect to the flow, the waves are actually stationary. Okay? So, the waves are riding on the flow, and then you can have a situation where the flow is actually faster than the speed of sound. So, somehow the flow is over speeding these disturbances, and we will see that there is something called the the sonic cone. The zone of silence, the zone of influence, and all these things we will see that will come out as a consequence of these the velocity of the aircraft or the object being larger than the velocity of sound, but that we will keep it for a slightly later discussion. But Mach number is defined as u by a, and when you have flow coming onto the airfoil, because of certain reasons which we will again talk about in follow up discussions, the velocity on the top of this airfoil is actually faster than the velocity upstream. So, what happens is, for if you think that the temperature of the flow is not changing, in fact, in most of these incompressible flow theory where we apply Bernoulli's theorem, temperature does not even enter the picture. So, you think of an isothermal flow field. Okay. So, whatever Mach number you have, if the flow is accelerating here, say at this point the flow has reached a very high speed due to acceleration, the Mach number here. So, say Mach number at point A, say Mach number at A and Mach number at B. B is let us locate the point B somewhere here, okay, point B. So, I am saying that the flow, once it turns around the stagnation point, it accelerates on the front portion of the wing, and it comes to a point where the flow speed is maximum, and then the flow again starts decelerating. So, if you again think in terms of that Bernoulli's theorem, which we will prove in our subsequent lectures, if you assume your Bernoulli's theorem to hold, then if your flow has reached the peak velocity here, then your static pressure has reached the lowest point here, because P plus half rho u square is equal to constant. So, if your u has become very high, and I am saying that at this point B point on the airfoil, you reach the highest velocity on the airfoil due to the acceleration. After that, flow again decelerates. Okay. So, flow accelerates, reaches a highest speed point, and then it decelerates. Now, what will happen is, the Mach number at A and Mach number at B, if you plot these two numbers, when Mach number at A is say 0.33, Mach number at B perhaps was 0.33. I am just pulling out some numbers. When Mach number was 0.4, this one was say 0.5. When Mach number was increased to 0.8, suddenly we see that Mach number at point B has become 1. So, this is interesting situation, that is your free stream Mach number. So, assume that the point A is located sufficiently upstream from the airfoil. So, in this picture my A point looks almost like close to the leading edge, but so go a few chord lengths upstream, so that the effect of the airfoil is not felt at that point. I mean effect will be felt, but the effect is not significant. So, if you go there and you find your Mach number, and you see that the Mach number is showing something like 0.8, and you come to the point where the flow has accelerated to the maximum velocity, and Mach number there has become sonic for the first time. So, then your MA, so this Mach number is known as Mach critical. So, what is critical Mach number? First of all, what is Mach number? Mach number is the speed of the flow by local speed of sound. So, U A divided by A A. So, that is your M A. What is M B? U at B divided by A at B. Now, A at A and A at B are the same, because speed of sound depends on the temperature, and as I said, in isothermal flow, in flow fields like this, temperature changes are negligible. So, we do not even consider temperature as a variable here. So, what happens is your Mach number here is less than 1, but here you are reaching Mach 1. So, this is that that transonic thing that we showed you in one of the slides before, that is near Mach 1. So, in the Mach number line, if you remember, we indicated an important Mach number 0.3 and said some compressibility effect shows up above this. Then we did Mach 1, of course, sonic subsonic boundary, but we also said that around Mach 1 you have this window of Mach number ranging from 0.8 all the way to 1.2, again loosely defined. It does not need to be 0.8 and 1.2, it can be ballpark away from those numbers. This window was called transonic, and part of the reason is this region. So, if you look at this one, so this vehicle is now flying in the transonic window, where although the free stream Mach number is less than sonic, there are portions on the wing that have reached sonic speeds. Okay. So, that is why something like 0.8 is the beginning window of transonic flow Mach number. That is, at Mach numbers around say 0.8, as the flow goes over a vehicle geometry, say the fuselage or the wing, primarily the wing, in the top surface the velocity increases and it can reach sonic speed. So, Mach critical is that Mach number where flow becomes sonic for the first time, and it somehow defines the start of that transonic window. So, that is critical Mach number. Now, if you plot the drag on this, so we have not talked about drag on a airfoil yet, we will spend enough time on the drag of an airfoil, but at this point just for the sake of general knowledge, as you just take it for granted. Of course, we have to show it in detail that if you now accelerate this wing beyond that Mach critical, what will happen is, right now when it is Mach critical, so right now when it is Mach critical, M critical, you have reached sonic point somewhere here for the first time. If you go beyond Mach critical, pockets of your flow actually has become supersonic, and you have very faint shock wave that are forming on the top surface. Then at some point there comes this drag divergence Mach number. So, you first start flying at a low enough Mach number, then you keep pushing your throttle, you reach critical Mach number, which means that the free stream Mach number is still subsonic, but somewhere on your wing surface you are reaching Mach 1 for the first time. Now, you pull your throttle even more, and at Mach critical you reach just sonic condition on one point on the wing. Now, as you have increased from Mach critical to some other Mach number, but still less than 1, okay, you have created a pocket of supersonic flow and a feeble shock wave. If you push it even higher, but still lower than sonic Mach, well, still the velocity is still the free stream Mach number is less than 1, you will reach a point when you will see that the drag on this airfoil becomes immense, and it does not really become immense, it starts becoming immense. So, if you look at this figure, so at this point it is a bit haphazard, but so I am talking about the purpose of sweeping back the wing. Okay, look at this one. So, C d is the drag on the airfoil given by this expression, drag divided by half rho infinity square u square s. In incompressible flow, sometimes we do not give the subscript infinity because rho is constant. So, there is nothing called free stream density and local density. So, rho is constant throughout the flow field. So, we do not write any infinity subscript for density, but nonetheless you see that C d as a function of Mach number holding angle of attack and Reynolds number of the flow constant. So, we will see again in Buckingham's pi theorem, why do we have this tendency of plotting CD versus m infinity and holding some non-dimensional parameters constant? Why can we not say drag as a function of velocity holding say surface area and density constant? So, there is a very powerful reason why we like to move to CD and m infinity. Remember that if you have CD, if you have m infinity, you can still figure out the value of drag, right. If you know CD and you know the definition of CD, you can still calculate drag from. So, you simply have to multiply CD by this term to get drag. So, it is not that we have lost information on drag or lost information on the velocity of the flow, but you will see that the Buckingham's pi theorem will give you a very powerful tool to do two things. One is to reduce the number of independent variables in an experiment and to find somewhat meaningful non-dimensional parameters that could be important to a problem. We will see that in some subsequent lecture, but here I wanted to draw your attention to the CD. So, again I said small d is for the drag coefficient of an airfoil. Okay. So, what you do is, you suppose this is your wind tunnel wall, this is the other of the wind tunnel wall. Of course, you have a small glass window to look at the wind tunnel, what is happening inside the wind tunnel. So, let us assume that this is your glass window. I should be making it transparent, but nonetheless making it transparent will be a little weird. So, let us color it blue and let us just say that is the glass window through which you can see your setup. Now, air is blowing from this direction to this direction, and what you have done is you have mounted your airfoil. Remember, I said from end to end. If you by mistake put a gap between the, so see this end, or you can say this tip and this tip. Okay, let me at least draw the cross section of the airfoil. Okay. Okay, suppose you have an airfoil of that cross section mounted here, and the tips are flush mounted. Flush means it is almost sealed with this wall, so that there is no connection between the lower part of the wing with the upper part of the wing around the tips. So, there is no, if you start seeing, suppose you introduce some smoke here, sometimes in flow visualization you do that, you introduce some smoke and you see some kind of a vertical motion is happening. That means your this wing that you have not really mounted it flush. Okay. So, you need to make sure that it is flush, and then again you run the visualization and you see that these there are no trailing edge vortices, because if you have these trailing edge vortices, you are really running an experiment for a finite wing. Okay. Now, so we put this thing of constant cross section that is of a particular airfoil geometry. So, you will see that just like the IUPAC nomenclature for organic compounds, even for airfoils there is a kind of nomenclature, and if you can read the nomenclature, you can actually, a lot of information about the airfoil is built into that nomenclature. Okay. So, if you see an NACA 6-digit number, these digits have some significance. For example, one digit might be telling you what is the thickness of the airfoil, one number might be telling you what is the camber of the airfoil. We have not talked about these things, but again there is no way you will go through a course in Introduction to Aerodynamics without knowing what is camber and what is thickness of an airfoil. So, we will come to those things at some point, where I think that those will be critically required for the discussion. I will describe that, but where I think that it is not critical to the discussion, it is good to know perhaps. There sometimes I might miss out on those things for the time being. So, now, so you run this, you measure the drag force, say with some kind of a balance, and then you divide it by half rho u square. You can find these from your wind tunnel calibration charts, that what regulator setting is what velocity in the test section, half rho u square, and S, which is the reference area for this kind of tests. See, for a finite wing on an aircraft, you look from the top and you find what is the projected area of the wing, you extend it into the fuselage and you see what is that area. So, that is your reference area. In this case, for the infinite wing or the 2D wing or the we say airfoil, just for the airfoil, what you do is S is given as C into 1. So, C is the chord length and 1 is unit span. So, here we just think of unit span. Okay. So, chord, so this is the chord length from the root to the tip. So, that is your C and that is your 1. So, essentially you are using this portion as the planform area. So, for a 2D wing, sorry, for a airfoil or an infinite wing, when you divide by that S, which is the reference area, you are really dividing by chord into unit span, whereas for the finite wing you take the entire planform area. So, you get your CD and you are, so remember you are holding the angle of attack the same, Reynolds number the same. Okay. Reynolds number we have not talked about, but I think some of you are aware of, is given by rho u L by mu. So, density, velocity, viscosity and L is some characteristic dimension, characteristic length scale. So, you have to hold, you are holding Reynolds number constant, you are holding the angle of attack constant. Remember what is angle of attack? In a wind tunnel, if this is the, sorry, let us do it here because that will interfere with my picture there. Okay. So, now you, okay, let me go back to blue because we were doing the wind tunnel viewing portion in blue. So, I am now showing you what I am seeing. Okay. You are seeing something like that. So, that is your airfoil cross section and that is flush mounted on the wall of the wind tunnel. So, it is actually flush mounted on the glass window on this side and it is also flush mounted on the glass window on that side. Now, what is the chord of this airfoil? So, if you join the trailing edge with the leading edge and extend like that, that is the chord line. Now, in the wind tunnel, your velocity would most probably be horizontally directed. Okay, you should go a little upstream, because if you come very close to the wing, because it is a subsonic testing, the presence of the wing will influence upstream, because flow will start moving away from the wing a little upstream of the wing. So, but nonetheless you know what is V infinity, and then the angle between the relative wind and the chord line is the angle of attack. Okay. So, these definitions are important. So, when you run an experiment, you set the angle of attack constant. In some experiments such as this one, for example, angle of attack here, angle of attack here, here with a knob perhaps you are changing this angle, holding other things constant, but in this particular experiment you want to see CD versus Mach number. So, you have kept your angle of attack constant. So, so remember this is the Mach critical, I said, that is the free stream Mach number at which a point on the airfoil reaches sonic condition for the first time, and typically it is, experimental data has shown that suppose you have maximum thickness here, for some airfoils the position of maximum velocity is located say at 11%. So, x by c 0.11. So, it is okay, this is not a universal constant, it depends on airfoil, but so just keep in mind that the position of maximum velocity is not always at the position of maximum thickness, okay, just FYI. So, at this point your m infinity is such that m at this point has become 1. So, m infinity is MCR. Now, look at what is happening to CD. As you increase your Mach number, you reach this Mach number called m drag divergence. So, drag divergence Mach number, and see what is happening behind it. The drag is rising up at a very steep rate, and this is where you have sonic free stream condition. So, Mach number 1 in the free stream. So, Mach critical is about 0.8, this is of course Mach 1, and Mach drag divergence occurs somewhere in between 0.8 and 1. Again 0.8 is not an universal number, it will differ from airfoil to airfoil, but nonetheless ballpark it is somewhere south of Mach 1, could be Mach 0.7, could be Mach 0.75, could be Mach 0.85, etc. But drag divergence lies somewhere between critical Mach number and sonic free stream Mach number, and at this thing you see it is not that the drag becomes enormous, but the drag starts becoming enormous. In fact, I think I mentioned it in one of the early lectures that for a long time in the 1930s and mostly in the 1930s and perhaps in some portions of 1940s, the aeronautics community actually had this apprehension that man-made air vehicles will never be able to fly above Mach 1, and part of the reason was this plot. That is, you see that your CD is growing at a very steep rate, and in fact, there is a way to show that CD is actually equal to scales with 1 by square root of 1 minus m infinity square. Well, essentially Cp scales with that number, but I will show in a later slide that CD also gets influenced by that Cp. So, Cp becomes extremely steep, scales with Cp proportional to 1 by square root of 1 minus m infinity square. So, you understand that as m infinity goes close to 1, your Cp becomes really high, and if you have flow separation, your drag on your body can be enormously high, and it can actually become infinite. Now, the problem is this approximation of 1 by this division by 1 by square root of 1 minus m infinity square, that is becoming infinite at m is equal to 1, is not valid at m is equal to 1. But the early mathematicians, I am sure the mathematicians may not have overlooked this, but engineers who looked at these mathematical results and jumped to conclusions, they did not pay attention to the limitations or the the assumptions of this theory. So, that whole idea of being proportional, Cp being proportional to 1 by square root of 1 minus m infinity square, which leads to very large drag, and I will show you step by step why that happens. At this point, essentially I want you guys to hear all these things once, because if you hear all these things once at the start of the semester, your brain will be able to process and connect other phenomena that I will be talking about to these bits and pieces. So, the problem was that that relationship where Cp is proportional to 1 by square root of 1 minus m infinity square, this was based on some assumptions which do not hold at that Mach 1. So, what ended up happening was you have this very large Cp, but it is not infinite, okay. Hence very large Cd at the sonic point, but not infinite. So, all you needed was a engine that can push you through that high drag region, and once you cross the Mach number 1, you see drag decreases, and we will talk about this whole drag thing in our next lecture. But at this point I want to just draw your attention to what is this drag divergence, and remember we are really discussing the sweeping back of the wing. So, what happens is when you sweep the wing back, instead of seeing, so what happens is if your wing is like this and you have say flow coming at a Mach number somewhere here or somewhere here, your sorry, let us just keep it slightly nicer, because so suppose you are flying at a free stream Mach number of this, where your section drag is somewhat like that high, it is a lot of drag on your vehicle. So, there is a trick to making the wing see a lesser Mach number. So, what you do is when you sweep the wing, so suppose this is the fuselage. So, instead of having a wing like this that is seeing the exact Mach number the vehicle is flying at, what you do is you sweep the wing back. So, now what happens is your wing sees a component of that Mach number. So, if you think of the component that is normal to the leading edge of the wing, so whatever component is normal to the leading edge, that one is actually less than the free stream Mach number. So, the leading edge will see, because you have swept the wing back. So, the leading edge, although the vehicle is flying at a certain Mach number, say the vehicle is flying at this Mach number here on the lower right, your wing will see something like this. So, the component that is normal to the wing. So, sweeping back has this advantage that your vehicle can still fly at high Mach number, but your the wing will not get into that high drag divergence situation. Okay. Now, let us quickly go through the remainder. Okay, here also I have to finish this portion. Okay. Now, there is something called geometric twist of a wing. Let me remove this one. Okay. So, again the line joining the middle points of all the chords is known as the mid chord line. If the mid chord line is a straight line, then you call it a straight wing. Okay. Here the mid chord line is not a straight line, you see it has it is bent. So, it is not a straight wing. but if you have a mid chord line, say if your wing is like a rectangle, this is your vehicle, mid chord line is a straight line. So, you say it is a, you know, it has a special name where mid chord line is not bent in any way. I think it is called a rectangular wing, but no, it is called a straight wing. Okay. So, okay, I am getting a bit confused here. It has some special name if your mid chord line is perpendicular to the axis of the fuselage. But here you see that the mid chord line has some angle with the fuselage, and these are some of the characteristics, and they have some influence. This term is known as the chord at the tip of the airfoil by chord at the root of the airfoil. So, this is the length of the chord at the tip, this is the length of the chord at the root, and this is given the name taper ratio. The thing is, when you talk about the design of an airfoil, you have to use some words, because you have to say what is the taper ratio to even make sense of if the the wing has the same chord all throughout, or the different chord at different distances from the fuselage, etc. Now, here you see that it is possible that I have the same airfoil cross section, but I have twisted this with respect to each other. So, the chord of A and the chord of B and the chord of C may not be in the same plane. So, then we say it is a geometrically twisted wing. Okay. So, we have the same airfoil cross section at these different cross sections away from the fuselage, but they are not in the same plane. You can also have a situation where here you use one particular airfoil, here you use another airfoil, here you use another airfoil, and these airfoils, if you look at the CL versus alpha plot, so let us just look at the not the flap deflection, but just the normal CL versus alpha. If you look at these, you see that when you deflect the flap, okay, hold on, what are we talking about here? So, when you have different airfoil cross sections, what can happen is your the alpha at which you have 0 lift can change from this section to section. If you go back to that plot, you see that okay, here suppose you have one as symmetric, but then some airfoil has this curve. So, see that CL becomes 0 at this alpha, or rather at this negative alpha. Now, if you have your one chord with a negative alpha of so much for 0 CL, if you have another chord with another negative alpha characteristics, then you say the wing is aerodynamically twisted. Okay. Your chord may be in the same plane. Okay. So, it is not geometrically twisted, but these cross sections have different airfoil shapes, because of which you have different alpha at which you have 0 CL. Okay. So, that is known as aerodynamically twisted. Now, this cambered airfoil, let us spend a little bit of time on this cambered airfoil. So, how do you, so do we have a symmetric airfoil somewhere? Okay. So, symmetric airfoil, you understand that it is same on the top and bottom of this chord line, whereas a cambered airfoil has some asymmetry. So, what you do is here, for example, you find the trailing edge, find the leading edge, you draw the straight line, you see the dotted line, that is the chord line for this airfoil. So, this one. Now, at different locations of the chord line, you draw perpendiculars that are cutting the airfoil top and bottom at some locations, and then you mark the midpoints, and then you join them. That line, of course, you know the chord line. The chord line is what you get by joining the the leading edge with the trailing edge of the airfoil cross section. Sometimes finding the leading edge point becomes a bit tricky, but nonetheless you can there are ways in which if you have a cambered airfoil with a difficult to find leading edge point where you will draw the chord, what you do is you find a circle of the smallest radius that can fit into the contour of the front part, and then you use that center, join the trailing edge center of that circle and extend it. But in most cases you will be able to find the leading edge, and just joining the trailing edge with the leading edge point gives you the chord. And the other construction, so you drew the verticals, the perpendiculars to the chord, found that for example, this perpendicular cuts the top surface of the airfoil at A and the bottom surface at A prime. Say this one is a D and D prime. So, these locations are D and D prime. Those distances give you the thickness of the airfoil. Okay. So, this when you draw those perpendiculars on the chord and find where they intersect the airfoil, the top portion and the bottom portion, then AA, DD, these lengths give you the thickness distribution of the airfoil. Sometimes we say this is a 10% thick airfoil. In this case, it is a 12% thick airfoil. It means that the maximum thickness is 0.12 times the chord, or thickness by chord maximum. Now, chord is fixed, so it essentially means T max by C is equal to 0.12. So, that is a 12% thick airfoil. So, when you go and purchase the airfoil, you have to mention what is the camber, what is the thickness, etc., because these things will control the characteristics, right, like the CD, CL curves. Also, these line joining the midpoints of those vertical lines gave you the mean line or the camber line, and the camber. So, the airfoil is positively cambered if the camber line lies above the chord line. In this case, it is positively cambered. It can also happen that your camber line or the mean line is below the mean chord, below the chord of this airfoil. So, in that case, it is called a negatively cambered if your mean line is below the chord. Similar to the thickness ratio. So, when you say it is a 12% thick airfoil, it means the maximum thickness divided by C, which is the chord length, is 0.12. Similarly, when you say 3% camber, it also means that the maximum distance of the camber line from the chord. So, you see that the start of the chord line coincides with the start of the camber line. Similarly, the end of the chord line coincides with the camber line, but the distance between the camber line and the chord line changes as you move from the tip to the root, the leading edge to the trailing edge of the airfoil. So, a 3% camber, for example, would mean that the maximum distance of camber line from chord is 0.03, okay, where C is the chord. Okay, so, I think that is a little bit of discussion about different parts of an aircraft. You should read them up from some other source as well. Now, I would like to go over these few slides from NASA's website on. So, NASA has a very nice like series of web pages where they have a very, of course, elementary introduction to aerodynamics, propulsion, etc., but nonetheless sometimes elementary knowledge is sometimes difficult to have. because not everything is explained in proper ways, or the source of explanation sometimes has some bias or mistake, but at least you can trust NASA on airplane parts and functions. So, that is the pretty much the topic of today's presentation. We are continuing from the last lecture. So, as we have already seen, of course, cockpit is for command and control, fuselage hold things together, carry payload. Okay. This is where you have your passengers. So, essentially the passenger cabin, the luggage deck below the passenger cabin, etc., are part of the fuselage. So, cockpit, fuselage, slats. So, remember we said that during takeoff and landing, sorry, let me stay away from that corner. Okay. If you remember, we said that in cruise your wing might look like that, although you have all these movable portions, all of them are like tightly fitted to one another, because remember your lift is CL times half rho u infinity square s. Now, when your aircraft is flying straight and level at cruise, you have a decent amount of u infinity. So, even with low CL you can generate enough lift to balance like weight, and depends on what you have to balance, but nonetheless in straight and level flight you need to balance weight only. So, you can fly at with less camber, less angle of attack, etc. However, during takeoff the general arrangement would look something like, remember the flaps are deflected, but not a lot. And at landing you have something of that sort. Okay. And remember the purpose of the leading edge slat was to introduce some high velocity air into this region, so that the flow does not separate. Now, we have not talked about what is flow separation, but like the next lecture will be on the drag of airfoils, and we will look at what is this flow separation, but at this point just keep in mind that your slats can open up. Of course, you get more S when this whole thing opens up, the S from the top, right, the platform area from the top view increases. So, S increases, CL increases, and of course, you prevent the stalling behavior by some by this injection of high energy air or high velocity air. So, slats, spoiler. Okay, we have not talked about spoiler. So, I think if you have seen out of the window of this civil aviation aircrafts, upon landing you will see this kind of small slots that open up. So, that increases. So, these things open up and stick almost perpendicular, well not perpendicular, but say 60 degrees or even more to the surface of the wing, top surface of the wing. So, what it does is it increases drag. You will see that how sensitive drag is to the lack of streamlined shape. Escher Shapiro actually in that series of videos on that National Committee for Fluid Mechanics films, he shows a very interesting experiment where he shows that the drag on a wire of a small diameter is same as the drag on a streamlined airfoil shape, even though the airfoil thickness is quite a bit. So, the streamlining of objects has very significant effect on the drag reduction. So, if you open up the spoilers, you have really thrown your streamlined design out of the window, and the amount of drag on both the wings increase immensely. Also, when the spoilers are open, you understand that you have created a gateway between the top surface and the top and the bottom surface of the wing. So, that also reduces lift, and the spoilers when they stick out they increase drag, and it is important after landing when you have to maintain enough friction of the wheels with the ground, and you also have to slow the aircraft. So, spoiler, change, lift, drag and roll. I mean, you can do differential spoilers and you can create some behavior similar to the aileron, because by doing a differential spoiler, that is, you deploy one spoiler, you do not deploy the other spoiler. That way you can change the lift in the two wings pretty much, that is what the aileron does as well when you deflect them in the opposite direction. So, spoilers can also help you in the roll motion. So, roll. Then you have the aileron. We have talked about the ailerons. These are the movable surfaces at the end of the wing. Remember, I said that if one aileron moves down, the other aileron moves up, or if this one moves down, then this one will move up. So, they move in opposite direction, because of which the lift on the left wing and the right wing in the neighborhood of the aileron becomes different. And since you see there is a significant moment arm, so if your axis of roll is somewhere through this, look at the arm. Okay, so normal. So, that is the moment arm. So, if you have difference in lift, then you end up having a rolling motion. Flaps you have seen, these are the flaps in action. Elevator, flap like thing, but on the horizontal tail. Rudder, also flap like thing, but on the vertical tail, and as you see, this changes the yaw. So, yaw is essentially this motion. Okay, it is difficult to actually show here. So, we will just revert to their view graphs. So, this is the vertical stabilizer, horizontal stabilizer, and that has the elevator. Now, winglet. So, I did not talk about this winglet. I think a lot of modern aircrafts have this winglet, but let us also look at the wing, that is what generates most of the lift, and you have the turbine engine that generates thrust. Okay, you need thrust to push the aircraft forward, and you need engines for that. The turbine engine is a popular choice. So, you have turbine engines. I showed you the SR-71 Blackbird that uses a dual turbojet ramjet. The ramjet is really an afterburner, but nonetheless it is still a ramjet engine. This one, most commercial aviation aircrafts use gas turbines. So, winglets, remember I talked about the situation with finite wings, that is, the pressure below the wing is larger than pressure above the wing, and that is on the average. Okay, so, that word is important. Pressure on below the wing on the average is larger than pressure on the upper surface. So, if you do not have this winglet, you have no resistance or hindrance to the movement of air from this high pressure to the low pressure, from the high pressure below the wing portion to the low pressure above the wing portion. However, if you put a winglet, it is almost like putting the end of the wind tunnel flush with the wing. Okay, so, you are almost carrying it with you. Of course, it is simpler said than done, but nonetheless it has been seen that including a winglet like that leads to some better performance in terms of the rolling the tip vortices, and we will see that these tip vortices have an influence on something called downwash. Downwash has some influence on the induced drag, and if you can somehow decrease the tip vortices, you will decrease the downwash, hence decrease the induced drag. So, that is why it is saying that winglets decrease drag. So, now let us quickly go through these series of pictures. You see that here the elevators are deflected up. So, flow is coming like this, going up, and as I said, the reaction force is down force, if this is your center of gravity, then your resulting motion will be pitch up, nose up. Here the aileron deflection. So, you see the aileron is deflected south. So, flow is getting diverted down, and you have more lift on this surface than on this surface. So, that leads to the rolling motion, and when you have the rolling motion, the bank angle. So, if you take the component of the lift in the normal and the horizontal direction, you can see that you get a centripetal force. You can look up some book in flight mechanics, or I think even your fundamentals of aerodynamics has all these things. Here this is the rudder deflection to the left of with respect to the pilot. So, flow is going in this direction. So, force is in that direction, and if you think of this is your CG, then using this as the moment arm, you can see that resulting motion is one of yaw. Essentially this will change the heading of the aircraft. Here spoiler action, you see that this increases the drag, and so it is a combination of increasing drag here, increasing lift here. So, the increase of lift on this side and lift is decreased here because your spoiler is deployed. Remember, spoiler is just like a window between the top and the bottom surfaces of the wing. So, lift decreases, lift stays the same. So, you have a rolling motion, and at the same time, since your lift has decreased here, this has more drag from the induced drag. So, that is counteracted by this drag because of the sticking of the spoiler into the main flow stream. Flaps and slats, we have gone through this, increased lift and increased drag. Stabilators, sometimes you do not have the conventional control surfaces, things are combined with each other. Okay, so, I think that is where we will close for the day. I would strongly encourage you to look up a book or even like a YouTube video that explains the different parts of an aircraft. So, thank you very much. We will continue in the next lecture, where we will go through the drag on wings and how to reduce drag on wings. Thank you.